Welcome to lecture 14. In this lecture we will be continuing on the discussion that we have been doing in the last two lectures. So in this lecture we will be talking about the electrostatics of p-n junctions. So basically we'll try to answer the question as to what is the width of the depletion region determined by. So we will try to address that question quantitatively. All right. So today's lectures follows section 4.1.4 and 5.1.4 and 5.1.5 of the textbook by Pure. All right. So again, the depletion in a p-n junction at equilibrium, meaning that the voltage V equals to 0, and we have seen that the holes from the p side will recombine with the n electrons in the n side. Now the question is that how long will this recombination go on, meaning that what determines the width of the depletion region. So will it continue until the entire n region and p region is depleted, or there is a certain width after which this growth of the depletion region will stop? So that's the question that we will try to answer in this lecture. So here we have a p-n junction at equilibrium, meaning that the voltage applied is 0. So here this is the x direction going from the p side to the n side, and we'll plot three quantities. So first here we will plot the charge density, fixed charge density. So first plot will be fixed charge density, and so say the width is like this. This much is the width of the depletion region in the p side. So this p side, basically the holes have moved there, so this is all negative, and the so the value of the fixed charge density will be QNA, and the unit is coulomb per meter square. And say on the n side the depletion is like this, and the n side this region is positively charged, so the depletion will look like this, and this is plus Q and D. So we are using subscript of small letters NA and ND. Okay. And say this width is negative WP and this is positive WN. So these are the depletion widths in the P side and the N side. Okay. So now the first thing is that based on charge neutrality, we have QNA WP equal to QND WN. So basically it means that all the negative charge on the P side are compensated by the positive charge in the N side. Okay, so now what is the electric field? Now the electric field, we can calculate the electric field at this interface. Now at this interface the electric field is maximum, because on the left you have this much of charge and the right you have the highest amount of charge. So basically the interface x equals to 0, on the two sides it has the highest amount of charge, and as you go towards this side the electric field will decrease. Also as you go towards the negative x direction the electric field will decrease. So the maximum electric field is simply the depletion charge divided by the permittivity of vacuum multiplied with the relative permittivity of silicon. Oh, so what is Q dep? Q dep is basically QNA WP equals to QND WN. So this is the total amount of charge, this is the depletion charge. So what we can write is E max is Qna Wp divided by epsilon naught epsilon silicon equal to Qnd Wn over epsilon naught epsilon silicon. Okay. Now this is E max, and this is negative. In this, at least in this plot, we have plotted it negative because we say the electric field in the positive x direction is positive. So this electric field will be on the negative x side, x direction. So we have plotted as negative, and this electric field at this edge, all these electric charges are compensated. So electric field will be 0 if you are at Wn. So the electric field will linearly decrease from negative E max to 0. And similarly, it will go from E max to 0 to negative Wp here. Okay. All right. So now we have seen that when we are doing Morse electrostatics, electric field is simply dV over x, or let's say this is psi. So psi is the electrostatic potential and so psi is basically the integration of electric field with respect to the position x. So at any given position x. Okay. So if we simply integrate this, then what we will have is this. So we are just integrating E max as a function of x. So this will look something like this. Okay. All right. So what we are interested in is what is the value of this much, which is basically the electrostatic potential across the depletion region in the p side, which we call psi p, and this much. So this is this much, and then here psi n, what is the electrostatic potential across the depletion region in the n side. So and then what we call is this, that what is the electrostatic potential across the entire depletion region. This is psi, and psi is simply psi p plus psi n, and this is equal to, so now what is psi p? Psi p is basically integration of psi in the p side. So it's a triangle, so basically phi p will be the area under this triangle here, and the area under this triangle is simply half of E max plus Wp, and similarly psi n equals E max multiplied with psi n square. And what we say is that the drop of the change in the electrostatic potential across the depletion region is what we called built-in potential. So this is we call VBI, and this is called the built-in potential. All right. So now the same calculation is shown here. So here again the charge neutrality condition, then we derive the maximum electric field, and then the built-in potential psi p plus psi n, and simply psi p comes out to be this, and the total depletion width is W, which is Wn plus Wp. Alright. So now in this here we have expression for VBI in terms of Wp and Wn. What we want to have is an expression for W in terms of VBI, or an expression for VBI in terms of W. Okay, so here again from the charge neutrality condition we derive Wp is related to W like this, and Wn to W like this. So VBI, we replace Wp and Wn with these two expressions, and finally what we get is this: VBI is proportional to the square of the total depletion width, or the total depletion width is proportional to the square root of VBI. Okay, so what do we get from all this calculation? What we get from this calculation is that this W is determined by this built-in potential. So for a given depletion width, we can have a certain VBI, or for a given VBI, we can have a certain W. Now it appears so that for a given doping density, there is a certain VBI. In other words, VBI is set by the doping densities of the P side and the N side. And based on that doping density, or based on that value of VBI, our depletion width is set. So it's not like that this W can increase indefinitely, because if W has to increase indefinitely, your VBI has to increase indefinitely. But VBI is actually a constant value given by the doping densities of P side and N side, and that value of VBI actually sets the value of W. And this is what we are going to see in the next slide. So to understand what VBI is, so let's look at the energy band diagram of a PN junction at equilibrium at V equals to 0. Now this is what we have seen in the last lecture, that this is the energy band diagram before the contact is made, and after the contact is made, if we fix the energies in the N side fixed, then the energies in the P side will have to go up such that the Fermi level of the N side and the P side lines up, because at equilibrium the Fermi levels on the both sides will be lining up, and the energy band diagram for the PN junction will look like this. This is what we have seen in the previous lecture, and VBI is basically the barrier height. So the barrier height is QVBI, which is equal to this value here, and also this is the same for this side here. And in the previous case, before the contact is made, VBI can also be defined as the difference between the Fermi levels before the contact is made. So now let's look at how the electrostatic potential is related to the energy band diagram of the PN junction. So what we have said is that this gap between EFN and EFP is equal to QVBI, and this is the energy band diagram before the contact between the N and the P type semiconductor is made, and this is the electrostatic potential profile. Alright, so what happens is that the EC essentially after contact essentially becomes EC prime X, which is the new AC after making the contact, is the old EC minus Q of psi X. So basically what you need to do is subtract Q multiplied with psi S from EC to get the EC after the contact is made. And similarly for EV, the new EV after the contact made is the old EV minus Q psi x, and after the contact is made, this is what it will look like. So you have subtracted psi s from the old ECs and EVs to get the new band diagram. Alright, so again, this is the electrostatic potential, and the difference of electrostatic potential on the N side and the P side equals to QVBI, and multiply QVBI with Q, and this gives you the barrier height for electrons looking from N side to P side, and for the holes looking from P side to N side. Okay. Now, what is it that determines VBI? Let's try to understand what determines VBI. So, as we have said before in the previous slide, the difference between the conduction band and the two sides is Q multiplied with VBI, or the barrier height is VBI. So what we say is that QVBI is ECP. So let's say this is ECP, and this is EVP, and this is ECN, this is EVN. So, and say this is the depletion width minus WP, and this is the depletion width in the N side, WN. Right, so these are the depletion width, depletion regions in the N side and the P side. So X equals minus WP minus ECN, X equals WN. Alright, so let's say we call this EC P naught, and this is what we call ECN naught. So ECN naught is the value of the it's the conduction band edge where the energy bands are flat outside the depletion region, and similarly ECP naught is the conduction band edge outside the depletion region where the energy bands are flat. All right, so now when we are discussing semiconductor physics, what we said is this, that for the N side, so let's first do the N side, the majority carrier density is electron, which is equal to the doping density Nd, and this is equal to Nc multiplied with EF n minus ECN 0 over KT. And for the P side, what we have is P, and this is equal to Ni square over Na, and this will also be equal to Nc e power EF P minus ECP 0 for KT. Okay, so say this is 1, this is 2. So if we now simply divide 2 by 1, then what we get is this Ni square over Na Nd equal to e power something over KT, and this something is So now EFN and EFP are equal, so simply they will cancel out. So finally what we will have is, so 2 is up, so ECN 0 minus ECP 0. So in other words, what we will have is ECN 0 minus ECP 0 equal to KT ln Ni square over Na Nd. So using this equation, QVBI equals ECP 0 minus ECN 0. What we will get is KT ln Na Nd over Ni square. So what we have seen is that the built-in potential is determined by the doping densities on the two sides of the p-n junction. All right. So finally, this is what we have gotten. The built-in potential, the value of the barrier is given by the doping densities on the two sides of the p-n junction, and this VBI determines the width of the depletion region. So essentially it means that this depletion region cannot grow indefinitely, meaning that it will not be the case that this depletion region will grow until the entire p-type and n-type semiconductors are depleted. Rather, the depletion width will be determined by the built-in potential, and the built-in potential is determined by the doping densities of the n side and the p side. Okay. So again, the same figures drawn here again, just so you get a better understanding of what's going on. And here EI is the intrinsic Fermi level, which we did not draw in the previous curves, but this is basically the almost the midpoint between the conduction band and the valence band for the p side and the n side. All right. So now a quick quantitative calculation. So we were given the values of the doping on the p side and the n side. What you are asked to calculate is the built-in potential and the depletion width, and these are the equations: built-in potential and the depletion width. So very simple, just plug in the numbers here and you will get the value of VBI here to be 0.9 volts, and then plugging in this here you will get the depletion width. Now note that this value of KT by Q, this is a voltage. So KT is in electron volts and KT by Q is in just volts. And at room temperature, KT by Q is equal to 0.026 volts. So this is one thing that you have to remember, and Ni in this case we have taken it to be 10 power 16 per meter cube. Now let's look at what happens to the depletion region when you forward bias it. So apply a positive voltage to the P side with respect to the N side. Now in the previous lecture you have seen what happens qualitatively. We have said that the depletion width decreases as you increase the forward biased voltage. Now here we will see the how the depletion width quantitatively changes with a forward biased voltage. So again this is the p-n junction band diagram for a zero applied voltage in equilibrium, and if we apply a positive voltage to the p side, forward bias it, the Fermi levels will no longer be lining up. There will be a difference between the Fermi levels in the two sides. So if we compare them, there will be a difference between them, and this difference is equal to QV, and V is the applied voltage. So if we write it, then it will be QFP minus EFP minus EFN will be equal to minus QV. All right. So now what will happen to the barrier height? So the barrier height previously was QVBI, and this time it will be QVBI minus V. So the barrier height will decrease by an amount QV. And the same for the valence band, it will decrease by QVBI minus V. And as a result, the depletion width equation, in the depletion width equation, VBI will be replaced by VBI minus V. Now it clearly says that if as the V increases, the VBI minus V will decrease, and as a result the depletion width increase. And at least theoretically, when V is equal to the built-in potential, then W will be equal to 0. Now in reality it's not possible to apply a voltage equal to the built-in potential across a PN junction due to many reasons, mostly due to the contact resistances and the resistances of the p-type semiconductor, n-type semiconductor. But at least theoretically, the depletion width will go to 0 when the voltage is equal to VBI. All right. So now let's look at what happens in the reverse bias. So again, there is a typo here. So this should have been reverse bias. And in the reverse bias, what we have said in the previous lecture is that when the voltage at the positive side is negative with respect to the n-type semiconductor, then the depletion width will increase. And in terms of band diagram, what will happen is that the Fermi levels in the n side and the p side will no longer be lining up. Rather, there will be a gap between them, and this gap between them is again QV. So again, if we write it, QFP minus EFP minus EFN equal to minus QV, and V is negative here, so EFP will actually be larger than EFN, so it will be higher in this case. The Fermi level in the p side will be higher than the Fermi level in the n side, and the barrier will now be QVBI minus V, but V is negative here, so it will be equal to QVBI plus the magnitude of V. And similarly, for the barrier height in the hole at the valence band side, it will be equal to QVBI minus V, which is equal to QVBI minus magnitude of V, plus magnitude of V. And we can clearly see that as the reverse bias voltage increases, the depletion width will increase, because VBI minus V and V being negative will increase with the magnitude of V in the reverse bias increasing. All right. Let's end this lecture with showing some calculations for as to how the depletion width will change in the forward bias and the reverse bias. So here we have a PN junction with the doping densities like this on the NP side and the N side, and equilibrium. Here this is the charge density for the N side and the P side, and this is how the electric field looks like. The electric field has a maximum at the interface between P-type and N-type region, and this is the electrostatic potential, and this is the band diagram. And note that the P side has a higher doping density than the N side, and the higher the density is for one side, the width of the depletion region in that side will be smaller. So here the P-type doping is higher than the N side doping, and as a result the depletion width in the P side is smaller than that in the N side. All right, so if we now apply a forward bias, we see that the depletion width has decreased. so did the electric field here, and also the band, the electrostatic, the barrier height actually decreased here by an amount of 0.2 volts here. And as we further increase the voltage here, we see that the depletion which has further decreased, the maximum electric field is also decreased, and the barrier height has also decreased. Okay, so now let's see what happens if we apply a sinusoidal wave which is superimposed on a DC voltage across a PN junction. So this is how the voltage is changing as a function of time, and you can see that as the voltage is increasing, the depletion widths are decreasing. On the other hand, as the voltage is decreasing, the depletion widths are increasing, and the barrier heights are also increasing. All right. So in the next slide, again we were showing the all these quantities for equilibrium, and the point is to show what happens in the reverse bias. So in the reverse bias, here we have applied a negative 5 volts, and what we can see is that now the depletion width has increased, so has the maximum electric field, and so did the barrier height.